Let's do another example now about internal resistance. And let's use an example of a couple of car batteries, one that's good and one that's dead. With a dead car battery, that tends to happen because the chemical reactions have changed the internal resistance of the battery. So let's say that we can connect a good battery with a potential of 12 volts and an internal resistance of 0.01 ohms. We can connect that in parallel to a dead battery with 8 volts and 0.5 ohms. And that's all going to be connected to the starter motor of the car, which has a resistance of 0.505 ohms. So let's ask, if we just had the good battery by itself, how much current would that drive through on its own? So let's draw a circuit diagram with just the good battery, and we haven't connected it to the dead battery. So in that circuit, we would just have the good battery with a 12 volt potential, plus to minus. We would have the internal resistance R equals 0.01 ohms, and we would have the external resistance of the starter motor 0.05 ohms. So we know that the battery is going to put out a current I. We can write our Kirchhoff's loop rule where we're coming around the loop this way. In our loop rule, we have a potential increase due to the good battery of 12 volts because we go from the negative terminal to the positive as we go around our loop. We go through the battery where our loop direction matches the direction of our current, so we get a potential drop. So we've got minus I times the resistance, 0.01 ohms. And we also have a potential drop over the starter motor of I times 0.05. And all that together has to give us 0. So then our current is going to be 12 volts divided by 0.06 ohms, or 200 amps. That is a lot of current. That's why you should always be careful if you're giving somebody a jump. Okay, so that's part A. Part B, how much current could the dead battery by itself give to the starter motor? Let's do that circuit diagram. So we've got the dead battery, its internal resistance, and the external resistance. So we've got 8 volts here, 0.5 ohms here, and 0.05 ohms here. The battery sends out a current. We can write our loop rule. 8 volts minus the current times 0.5 ohms minus the current times 0.05 ohms gives us 0. So I is going to be 8 volts divided by 0.55 ohms equals 14.5 amps. That current is a lot smaller, and that's not going to be enough to start the starter motor. Okay, part C, let's attach the good battery to the dead battery. Let's do the attachment in parallel. Then let's see how much current goes through the starter motor. So, new circuit diagram. 0.1, 12 volts, 0.5, 8 volts. Sorry if you can hear that in the background. My dog heard someone barking outside, and now he's helping out. Okay, 0.01 ohms, 12 volts, 0.5 ohms, 8 volts, and 0.05 ohms. So we're going to have to follow our process of Kirchhoff's laws here. Let's label our currents. We'll call the first current I1. And if we're labeling our potentials, it goes from the negative end of the battery to the positive. And then through our resistor goes plus to minus. Our current gets to a junction and it splits. Some of the current can come down. We can call that I2. If we're labeling in our terminals, so the top part of the battery has a high potential compared to the lower battery, to the lower end. Sorry, I was thinking ahead about the battery. The long line for our battery indicates the plus terminal. The short end is the negative terminal. Then our current, part of it split to go down through the dead battery. Part of it goes on through the starter motor. Let's call that current I3. Going to need to pick a couple of loops here. For loop 1, I'll go with the left-hand side. So that's loop 1. And loop 2, I'm going to pick the whole loop for loop 2. So there's loop 2. And we'll write our Kirchhoff's law for both loops. Loop 1. Got to be really careful about the potentials here. It's why I was pretty careful to indicate the signs on everything, because you want to make sure that you get your drops and your increases done correctly. So starting with loop 1, the first thing we'll have is the battery. We go from the negative to the positive. We have a potential increase due to the battery, 12 volts. Then we get to our first resistor, 0.01. There is a potential drop because we go from plus to minus, and our loop goes in the same direction as our current. So we've got minus 0.01 times current I1. Then we get to our second resistor. Our loop goes in the same direction as our current I2. It goes from plus to minus, so that's a potential drop. Minus 0.05 I2. Then we get to our battery. Notice that our loop goes from plus to minus, so going with the orientation of our loop, which is down through this branch, we get a drop over that battery. So you have to be really careful about your signs when you're doing your Kirchhoff's laws problems. Thinking ahead, I know I'm going to have to do some algebra here, so I'm going to go ahead and I'm going to rewrite this expression and solve it for I2. So 12 minus 8 is 4, minus 0.01 I1 minus 0.05 I2 equals 0. So that gives us, did I mix up? Oh, I did mix up. I wrote down 0.05. It should have been 0.5. Okay, that's easily fixed. 0.5 I2, 0.5 I2. So 0.5 I2 equals 4 minus 0.01 I1. So I2 will divide both sides by 0.5. I2 equals 8 minus 0.02 I1. Okay, there's one equation we'll be able to use in solving our algebra. Our next equation will come from loop 2. In loop 2, let's go around our loop. So we get a potential increase due to our good battery of 12 volts. We get a decrease through the 0.1 ohm resistor, so minus I1 times 0.01. Then we get to the 0.05 ohm resistor. We notice the current I3 travels from plus to minus, so that's a potential drop. Minus I3 times 0.05. That all sums to give 0. I want to rearrange this equation and solve for I3. So I3 times 0.05 equals 12 minus 0.01 times I1. So divide both sides by 0.05 to get I3 equals 240 minus 0.2 times I1. There's two equations. I need my third equation. That's going to come from my current law, or my junction law. That says that the net current into any junction is equal to the net current out. I indicated a junction at the top of my diagram. Current I1 goes in, and currents I2 and I3 come out. So there are my three equations with my three unknowns. Now I can go ahead and I can solve the algebra, and I should be able to figure out I3. This page is a bit full, so I'll go on to the next slide. So let's keep solving with our algebra. I1 equals I2 plus I3. Now I2 is equal to 8 minus 0.02 times I1. And I3, is equal to 240 minus 0.2 times I1. We're trying to find the current through the starter motor. We're trying to find ultimately I3. So that's what we're after here. So let's have a look at our algebra. I1 is equal to 248 minus 0.22 I1. So then 1.22 I1 equals 248. I1 is equal to 248 divided by 1.22, which is 203.3 amps. So that's the current that now gets put out by the good battery. That's the amount of current that comes out. Part of it branches to go down through the dead battery, that's part D, and part of it goes through the starter motor. This problem asks for how much goes through the starter motor. So from our loop 2 equation, I3, the current through the starter motor, is equal to 240 minus 0.2 times I1. So 240 subtract 0.2 times 203.3. That gives us a current I3 of 199.3 amps. So remember, if it was just the good battery by itself, that drove through 200 amps and the engine would start. With the dead battery attached, we drive through 199.3 amps, and that's enough, and that will actually get the motor started. The last part of the problem asks, with the jumper cables attached, how much current goes through the dead battery and in which direction? So that means we have to find our current I2. And now here's a good place to stop and think about direction. We labeled the current as going from the top of the circuit towards the bottom of the circuit. And when we wrote our loop rules, we went by that convention as if I2 was going in that direction. When we solve for I2, if we get a positive value for our answer, it tells us that we guessed right. We did the correct direction of the current. If we get a negative answer for I2, it means we put in the wrong direction of current. So as it stands now, we've assumed that it goes downwards in that branch, so from the positive terminal of the battery to the negative. If we get a positive answer for our I2, we'll know that that's the correct direction. If we get a negative answer, we know it runs from the negative terminal to the positive. To find the magnitude of that current, we'll use the equation that we got from our loop rule when we wrote for loop 1, which was I2 equals 8 minus 0.2 times I1. We can fill in what we already found for our I1, which is that I1 was 203.3 amps. And that turns out to be 3.93 amps. That makes sense because that's a pretty big resistance compared to the starter motor resistance, so we anticipate less current. We got a positive result for our current, so that tells us that it flows from the positive terminal to the negative terminal that we showed on the diagram.